Today's presentation is a detailed comparison between the mechanical and electrical parameters related to polymer film and ceramic technologies. These are two of the most popular electrostatic capacitor technologies in use today. First, just a quick intro on myself. My name is Zach Kill-Smith. I've been with Quantic Pactron since 2017. I'm actually a mechanical engineer by education, but almost all of my professional experience has been in the power analog conversion industry, and especially with power capacitors specifically. Today we'll be giving a quick intro to Pactron and quantic electronics in general. We'll be reviewing the current trends in power conversion technology and what makes Pactron's proprietary technology, the multi-layer polymer technology, what makes that enabling technology going forward. We will also be comparing Pactron's MLP construction and better understand how it compares to other technologies that are out there, such as MLCC. We'll be discussing Pactron and what we're doing to sort of continue being a leading edge provider of multi-layer polymer capacitors going into the future as well. So first, a little bit of history on Pactron. Pactron has been manufacturing film capacitors in Lynchburg, Virginia for over 50 years now. In 2021, Pactron was acquired by Quantic Electronics. Quantic Electronics is an electronics-focused company with multiple verticals under its umbrella. One of those verticals being passive electronics, including Pactron capacitors. So what is a capacitor? A capacitor, let's start with the equation. It's a very simple relationship between the dielectric constant K of the insulating material being used between two conductive plates, the effective area of those plates, and the separation between them. In comparing electrostatic technologies, all these four factors can be taken into consideration quite literally. Even though the dielectric constant of some popular ceramic materials is up to 1,000 times, so that K value up to 1,000 times that of some of the most popular polymers, those same polymers have higher dielectric strength. So thinner plate separators can be used. So the technologies are very different, but the end effect is actually quite comparable. There are distinct advantages and disadvantages to each, and that is what we're going to focus on today. Some of the main use in electrostatic capacitors exists within the world of power conversion. That's both for snubbing, filtering applications, also for current driving applications for switch mode power supplies. As many engineers have seen, wide bandgap technology, that is new semiconductor switches, silicon carbide, gallium nitride, they're being used more and more widely in high reliability applications. This is to reduce size, weight, and increase power density of the power supply. By increasing switching frequencies, you can reduce the size and weight, but the capacitor technology required for these applications has to keep up with the frequencies and voltages that are now being used. Let's talk a little bit about a real versus an ideal capacitor. Every real-life capacitor has some parasitics. In the case of electrostatics, our main concerns are the equivalent series resistance, the ESR, and the equivalent series inductance, ESL. As we look at the different technologies out there for capacitors, there's really two main separators. You'll see on the left here, electrolytics and electrostatics on the right. We have high reliability offerings within the Quantic portfolio for each of these. Hybrid wet tantalums coming from Quantic Evans. UTC makes a number of high reliability ceramics of all sorts. And of course, we have the polymer film capacitors, multi-layer polymer from Pactron. The main focus today is going to be on comparing the polymer film MLP technology from Pactron and some competing ceramic and film technologies that exist. As you can see by this diagram, there's a lot of overlapping applications between different capacitor applications and their uses. The MLP, which is the specific technology that's sort of proprietary to Pactron, the stacked multilayer polymer capacitor, sort of overlaps what ceramics and polymer films can do. Similarly, if we look at voltage ranges, the sweet spot for the MLP film, sort of right in between what we see for multilayer ceramic and polymer film. Let's take a look here at the mechanicals, the cross section. If we're comparing a wound film capacitor, that is the traditional film capacitors that most engineers are familiar with, to Pactron's multi-layer polymer technology or stack technology on the right, wound film capacitors that you see on the left actually are composed of two continuously wound electrodes. That composition can create some internal stresses in the capacitor, especially during thermal cycling and self-heating. So think about when that capacitor is getting energized, thermal shock applications. Also, the manufacturing process means the winding offsets need to be rather large. For lack of better terms, there's a little bit of a sloppiness involved in continuously winding capacitors. It means the tolerances need to be bigger. So the effective capacitance area, you can sort of see this on the left here, is where the black bold electrodes overlap. So in the case of the wound capacitor, we're seeing about 1/3 of the effective area being used effectively as a capacitor. Now on the right, this is an example of stacked capacitor, an MLP capacitor. The stacking versus winding that Pactron uses reduces those internal stresses I was talking about. That allows us to use ultra-thin films. So we're decreasing that separation between the electrodes. Our capacitance density is increasing significantly. Precise stacking allows for smaller extensions that you can see on the left and the right of the lower right diagram. This allows to make the effective capacitor area much larger. This unique manufacturing process also allows for pure aluminum terminations and pure aluminum electrodes. No dissimilar metals exist within the capacitor body itself. That's a really big deal for lifetime. Also, we have perfectly parallel plates in our stack design. That allows for some lower inductances. The end termination of our stacked capacitor does create some disadvantage compared to wound, and I can elaborate on that later. Let's get down to the numbers now. Let's look at a real comparison here. In practice, how significant are these differences? Here's a comparison between a wound versus MLP cap. Both are 4.7 mic and 100-volt rating. You can see actually in the graph here on the right, the wound versus stack comparison. The resonant frequency of the stack capacitor is about 1 kilohertz higher. So if you think switching applications, that's actually very significant. Inductance reduced by almost half. ESR is about 33% compared to wound. So these are very significant differences that we're talking here. Let's go back to structural differences. The structural differences of the MLP truly do put them in a class of their own. Look at the list of things that we have eliminated just by moving to this proprietary technology. Air voids, epoxy fills, ineligible markings. These are all things that are very critical to the high reliability industry. And these are all problems that we've been able to solve, in addition to having just an electrically high reliability product, something that can outperform frequency-wise and temperature-wise. So let's take a look at the structure. We talked a lot about the structure of the MLP versus the wound film capacitor. Now let's take a look at the structure comparison between the multi-layer polymer film and the multi-layer ceramic capacitor. MLP is actually very structurally similar to the multi-layer ceramic, or MLC. That's what you see here on the left. There are distinct advantages to MLC ceramics and MLP capacitors both, and this technology has its place in the high reliability circuit. But you can see here, based on the mechanics, that they are structurally similar, and that plays into why there's some overlap in applications. So let's talk more about that. Since we're on the subject of mechanics already, let's talk about a known issue with MLCCs. That's cracking at the lead terminations. Ceramic material is, of course, a brittle material, and multi-layer ceramics are susceptible to cracking. This could be from various conditions, including thermal shock, handling during manufacturing, handling during use, board flex, also electrical piezo effects that could be caused by strong electrical pulses, specific waveforms that the capacitor is seeing, things like that. Here on the bottom left of this slide, you will actually see some cracked ceramic capacitor cross sections. You can see the solder fillet here with a well-defined crack. Typically, MLCs do result in short mold failures, meaning that when that material cracks, this leads to a high impedance connection that can cause arcing or sparking. Safety ceramics do exist. Actually, the example that we're showing here on the left is an example of a safety ceramic. If you look very closely, there are extended lead terminations to prevent that crack from causing a full short. However, any crack is going to take that capacitor out of the circuit. The dielectric that we use in MLP film capacitors is a flexible polymer. So the entire capacitor body has some level of flexibility. In addition, there's no significant piezo effect in the polyester dielectric that we use in our MLPs. The mass of a given MLP is as little as 25% of an equivalent value multi-layer ceramic. The MLP has outperformed equivalent MLCCs in numerous environmental tests, including vibration, shock, and board flex. This is a board flex example here. After 500 hours of testing, you can see that the product has still passed. Common to nearly all metallized film capacitors is the ability to self-heal, as it is called, in the event of a high voltage transient or even a mechanical activity that results in dielectric breakdown of the ceramic capacitor, of the film capacitor or polymer capacitor. The polymer dielectric material will actually fuse around this fault and isolate. The capacitor can then continue to operate after the clearing event with minimal damage to the capacitor itself. If you're comparing this to ceramic, most issues, cracking, faults in ceramics will lead to a short mode failure or cause the capacitor to be taken effectively out of the circuit. One continuing theme you will see in this presentation with film capacitors is that they're generally quite stable. This is loosely related to the low dielectric constant referenced earlier, the 1000x seen in ceramic versus the orders of 2 to 3 of K value seen in films, right? So that causes us to be very stable. Many of the electrical characteristics of dielectrics over temperature are nonlinear. The same can be said for polymer. PET temperature profile is also nonlinear. But the temperature coefficient, as you can see here in the blue line compared to the red line, is significantly lower. So we have something that's significantly more stable compared to X7R. And increasingly significant consideration as we go up in voltage is the DC bias effect. Now, with some types of X7Rs, there can be a decrease as much as 80% of your effective capacitance in the circuit at 400 volts, 40% at 100 volts. This, again, is loosely related to the high dielectric constant of the material, and the dielectric thickness of the material also plays a factor. dissipation factor. A continuation of trends here as well. Again, the reliance on capacitance from thin plate separation versus high K allows for a very stable relationship of dissipation factor over AC voltage. One very interesting thing about polyester and most film capacitors is there exists no use-related degradation mechanism with these capacitors. They may age from things like environmental moisture ingress, from crystallization over time or breakdown of the dielectric, but there is no age-based, age-related degradation mechanism like there might be with ceramics. So their effective lifetime is extremely long in the field. So far, I've been talking a lot about the advantages of polymers. Despite these unique advantages, there exists some very favorable properties in ceramics as well. That often makes them the primary contender for medium voltage applications in power electronics. The number one advantage, I would say, is, again, the high dielectric constant of some of the most popular dielectric materials. What this allows for is significantly higher capacitance density or smaller overall size. When you're designing anything, especially high reliability devices, size is critical. Also with ceramics, extremely high breakdown temperatures of the ceramic capacitors make them great for high temperature applications. And film is sort of moving in this direction. We've made a lot of innovations. So some films can go up to 200 degrees C now. But again, ceramics, very hard to beat temperature-wise. Let's see. Also important to note, more stable dielectric materials exist in the NPO side for dielectrics. So I've been focusing on X7R dielectrics, which have high cap density, but are not necessarily stable. They have a higher coefficient, if you will. There do exist alternatives in ceramics. The disadvantage here is that those more stable alternatives are also much higher in size. The latest advancements in ceramic technology are reducing dielectric thicknesses to as low as 0.5 micron, which is significant, increasing dielectric strength to as high as 35 volts per micron. So taking those into consideration, these values are actually approaching what today's commercially available film cap technologies are able to achieve. So in many ways, ceramic is coming up onto the same level as film. So later we'll review what film is doing about that. MLP still exceeds in the areas of mechanical robustness, weight, ripple current handling capability, and overall efficiency. So far, MLPs are still the leader in those applications. It will be interesting to see over time what niches film and ceramic capacitors continue to fill as electrical technology and topologies continue to evolve. Let's talk about space, since we are a high reliability manufacturer. Pactron's MLP capacitors have been used in space, but they do not fit into the MIL PRF 83421 performance specification. This is a performance specification typically used by NASA. NASA's qualified parts list, or QPL, is dictated by this MIL-PERF, at least for film capacitors, that is. But the MIL-PERF is specifically for hermetically sealed and axial leaded parts. By hermetically sealing parts and making them axial leaded, this restricts you to a wound technology. This increases the overall size of the capacitor by adding a very large case with glass to metal seals. So there are some disadvantages here. Meanwhile, the Pactron capacitor has been used. We've been able to demonstrate that the outgassing and the moisture absorption rates are acceptable for most space applications. And given that, we've been given, specific, application-specific approvals for use in space. One of the more interesting high reliability applications currently working on with the MLP is ion propulsion. So this is a very low power propulsion system for satellites and small space vehicles, basically to redirect their orbit. In this case, stacked ceramics were originally being considered for the same application, but they were having issues with piezo effects from the ion propulsion waveform, which was hammering those capacitors. They were not mechanically flexible and ended up cracking. This customer ended up trying our MLPs. They are mechanically flexible. They have no piezo effects. So far, they're still being tested, and they're still the top consideration for the application. Another interesting application that we've been working on, or example, would be the power dissipation factor of film capacitors in general. Ceramics, they're widely used in space. They can handle much more heat. They're volumetrically efficient, but the dissipation factors are typically very high. So for applications working in the vacuum of space, heat dissipation and circuit efficiency are very important considerations. One proposed MLP solution using a high temperature, ultra high Q dielectric actually came out with a DF of 0.08% at 1 kilohertz and maintained the operating temperature requirement that our customer was looking for of -55 to +125C in a vacuum. And the ceramics that they were investigating simply could not do that due to their heat output. So I can imagine that any high reliability, mobile, battery powered application that cares about weight, size, might benefit from those advantages. We talked a little bit about this earlier, but there's a very obvious trend in power electronics that's moving into high reliability power electronics now, and that is the introduction of wide bandgap switching technologies, namely gallium nitride and silicon carbide. Both of these are more efficient. They have lower rad susceptibility, so they're very popular for space applications. But they also require higher voltages, and they can operate at higher frequencies. So to take full advantages of these changes, the MLP is perhaps one of the few technologies out there to satisfy all the necessary conditions for high reliability applications, including extended temperature range and frequency. MLP film capacitors are continuing to advance along this semiconductor technology as things change. We are investigating new polymers that can operate past 200 degrees C. We're investigating new ultra low DF materials that can still operate to 125 C, 140 C, and above. So these are all geared directly for those wide bandgap markets. Another interesting technology, thin film deposition of dielectric material, a whole new manufacturing process that could disrupt the entire power capacitor industry. In my opinion, the future of stacked MLP capacitors is very bright, and I think we're seeing a bit of a renaissance here in our industry with the way that power electronics in general are changing. That concludes my presentation. I'm now going to open things up for questions.
Thanks, Zach. I have one question here. So you mentioned having no dissimilar metals in the MLP capacitor. What are the advantages of this, and why isn't everyone doing it?
Okay, that's actually a great question. Okay, so dissimilar metals can cause the metallized electrodes to corrode. If you look at the structure of a film capacitor, the electrode metallization is very thin. It's on the order of angstroms thick. The reason dissimilar metals are often used with wound films is due to flexibility and a lower melting point of the zinc. So this can be sprayed on easier to those materials. Now, in order to mitigate this galvanic process that can happen, a zinc heavy edge now needs to be added to the metallized layer. There's restrictions on how much aluminum metallization can then be applied due to the galvanics. So there's a lot of considerations there. The unique construction of our capacitor allows for pure metal aluminum terminations to be used. And by using aluminum terminations, we don't have to have any dissimilar transitioning metals to reduce galvanic corrosion within the electrode itself. The reason we can use that where others can't comes down to the stack technology and the way that we actually stack the capacitors in a group as we metallize the outsides of them to create the terminations. So again, very different process that allows us to create a much more high reliability product.
Great, thank you. The next question I have here is, why is capacitor efficiency considered so important when the parasitic losses seem so low compared to other power supply components?
Well, actually, when you look at some of the leading edge power conversion designs and the semiconductors that are used in them, especially for high power applications, 15 kilowatts and above, the driving capacitor efficiency is actually not so negligible at all. In fact, it's a pretty big consideration in the overall design. Also for bidirectional and resonant applications, that steady impedance over frequency and temperature allows for the converters to be used efficiently across a wider range. The alternate to that is to stack, multiple capacitors in parallel or multiple converters in parallel, and only operate a few at a time to mitigate that. As battery and renewable electric mobile applications kind of continue to increase, I can see this becoming a bigger and bigger consideration because when things are being powered mobily, every bit of efficiency counts.
Why is polyester the main film used in your capacitors?
Okay, great question. If you're looking at the film capacitor market in general, you'll probably see a lot of polypropylene out there, especially for AC applications. Polypropylene is limited to 85 degrees C typically. Its melting point is of course much higher, but given its self-heating ripple current ratings, generally limited to 85 C. You'll see some exceptions that go up to 105 C. We use a special type of polyester material that can operate in AC environments up to 125 degrees C. So Pactron is fully dedicated to the high reliability power market. Most of our customers do require a minimum of negative 55 to positive 125 degrees C operation. And with our unique construction, we can still use the polyester dielectric for AC applications. So that's the main reason that we use polyester. That being said, we have some new dielectrics that we are using for other applications, soon to be released as standard offerings too. Ones with ultra low DF, ones with ultra high operating temperatures, ones with both. So there are a lot of other options potentially out there. Of course, us being the high reliability manufacturer that we are, need to fully test them before they are released.
Okay. Why is there a voltage limitation on stacked MLP capacitors when compared to wound film?
Good question. And I think I mentioned that earlier in the presentation. Let me go back to that diagram quick, and hopefully if we look at these two constructions here, I mentioned that essentially the wound capacitor has two continuously wound electrodes, whereas the MLP has thousands of stacked electrodes that are individual. By having these wound, your high voltage area only occurs at one termination. With stacking, you have literally thousands of terminations to consider. So in order to create a very high reliability capacitor, we're sort of limited in voltage between the layers. We mitigate that by using a process called internal serialization, very similar to what MLC manufacturers will use for their higher voltage capacitors. But again, there are some considerations here. And the main reason we don't currently go above 1200 to 1500 volts in our applications is because, eventually that trade-off, there's a trade-off with just about any electrical component, right? Eventually that trade-off kind of meets a need, and the wound performs just as well as the multi-layer polymer in that case.
Okay, thank you. Last question we'll take. So early on, you talked about the MLP's significance in high frequency and resonant power supplies. I've seen plenty of resonant designs that don't use these. What makes them so special for this application?
Great question. Great question. I think we talked a lot about, what makes them special in general, but yes, other technologies exist out there, like your traditional wound films, right? A lot of the, bidirectional, inverter applications today are using wound film capacitors. A lot of the resonant power supply topologies are using wound films still. But there's restrictions here. Again, our company in general is focused on high reliability. If your customer is looking for, something that can operate over 85 degrees C, or if they are space restricted, the MLP provides the best choice. If you're looking strictly at wound capacitors for this application, they can often be used as long as that temperature rating is met. However, you might need to include extra capacitors in parallel in order to meet the ripple current requirements, or in order to meet the ESR requirements. So by doing that, you're significantly increasing the overall size of your converter. So when size, weight, overall efficiency are critical, the multi-layer polymer proves to be the best solution.